Hello, everyone. Okay, thank you for joining my talk. As he presented, I'm working in Jon Snow Labs, which is, well, a company in the United States that's doing a lot of research and work in healthcare and medicine. And I'm particularly a developer and data scientist for the tool I'm going to introduce you, which is Spark NLP. So first of all, I would like to know you a little bit more. I would like to know, for example, who have heard of Spark NLP before? Please raise your hand. So yes, it's quite a new library. It's been released, the first version, in October 2017. And well, it's an open source project, so it would be great. And who of you know already Spark or have worked with Spark either on Python or Scala? Okay, that's plenty. Okay. Okay, hope you find it interesting and well, exciting as well. So, okay, what am I going to talk about? I have only 25 minutes, so it's quite little time. At first, I'm going to take on, well, the previous presentation from Matthew. It was great, and to go a little bit backwards and explain why is NLP challenging and why are their problems like what they are. Second, I'm going to introduce Spark NLP and how kind of does solve this kind of problems. And third, I would like to go into a full example, which is what most interests me, so you know and see Spark NLP in action. I would like you to hear your feedback and, well, contribute and things like that. So that example is going to be applied in an example that you can access later on the website. So, well, the point of NLP is that, you know, we all speak many languages, and that means not about the language itself, but about the content of the language. And that's where NLP becomes difficult, because we might be talking about an academic language where words and context and sentences are very specific, and they have their own abbreviations and their own abstract and way of showing their data and things like that. We have financial language where, you know, it's maybe in the text we have plots and visuals that say more than 1,000 words, like cliche. Well, we have numbers and things like that, and it's a completely different language, even if it's still in English. It means things are spoken quite differently. We can even go to email language, which is something completely informal, full with hyperlinks, things that are specific to the body of the email, depending on what to use. If we use the raw email, it's full of rubbish content and things like that, apart from the body. Well, that's a little bit of why is that difficult, and that is what makes NLP difficult in some sort. The point here is that we cannot use like simply any model, any R model, and expect it to work for emails, and then suddenly expect it to also work on a financial form. So it's very important that when we want to go into production, we spend more time than anything else on getting the appropriate data to train the models and actually train them with that specific domain language. So it's very important because I've heard many people asking, hey, I have used your named entity recognition model on my data and it doesn't work. It doesn't find my new company name. Well, I mean, the model was meant to some generic, it's how to test it, how you can use it and get to know the algorithm. But of course, if you want to put it in action, you need to know your data, and you need to, like, as Matthew was saying, you need to annotate content, and you have a team of annotating content, or someone on Amazon Turk or whatever that knows also the field and gets communicated with data scientists and things like that. So that's also what makes, again, from the previous talk, machine learning something from learning from the example. So I hope that was a little bit fast introduction, but it's also because I want to get a little bit on topic of what Spark NLP is and what is focusing on it. So Spark NLP attempts to be an industrial grade NLP, completely based on the Apache Spark ecosystem. So that means that it can grow in performance and scale along Spark. It can be easy to reuse along that ecosystem, meaning that you can integrate it, move it, test it apart, aside, like tinker it. And it's also meant to be enterprise grade, meaning that you could create like production ready models that are applied to some specific content and try to make easy that learning part, which is usually the most complicated one. So, well, you know, easy in machine learning is a difficult word to say because nothing is easy, but at least not to get in your way of doing it. So it's built on top of Spark ML. Hope you know it. Spark ML is the machine learning library for Spark. This specific one is the one running on top of datasets. So it's not the old one now called MLlib, which was working in RDDs, and it was difficult because you had to work with structures and object content and things like that. So Spark ML library, as you know, is on top of the dataset or data frame API, and it's quite human to use. So Spark NLP is also open source, Apache 2.0 licensed, and it's ongoing active development and support. So super important as an open source project that's actually very new to attract new developers and enthusiasts to test it or to contribute it. So we are willing to help work together. It's an ongoing project, and I think it's very interesting, particularly for those that are recently started and would like to implement something new or get to know, because it's still a quite small project, but so that's an important point. So as I was saying, it's extending Spark ML. So you know Spark ML has two very important concepts, or three. Well, let's start with two, that are the estimators, that you know the estimators are the ones that are going through a training stage, which is called to a function called fit. And then that estimator is converted to a transformer, which is the trained estimator that's ready to transform some data from your data set into something that's actually your result. So Spark NLP does this, but aside of those estimators and transformers, which are like, for example, the n-gram calculator, word-to-vector, top modeling, logistic regression, and other estimators and transformers Spark has, it includes new related to NLP stuff. So that means part of speech tagging, named entity recognition, sentiment analysis, tokenization, lemmatization. So it's kind of trying to add to those same things, and it's, well, it actually works the same way. So these are estimators and transformers. Some are directly transformers, meaning they don't need training. They are ready to transform something. For example, the tokenizer. The tokenizer that we have implemented doesn't require to be trained. It has its own preset of rules, and it's quite flexible, so you can customize it for different languages, for example. But other models like the sentiment analysis or named entity recognitions are actually estimators, meaning that you need to have some label data and you need to customize your pipeline, which is the third concept I want to add, which is the thing that puts things together. So, well, this is integrating with the Spark dataset API, so it's the same as the also others. So here, a very quick pipeline example. Well, as you can see, the pipeline is the thing that's assembling or putting together all the estimators and transformers. And the good thing about the pipeline is that you can put together both estimators and transformers, and it's the same. So those that are estimators are going to get trained. Those that are transformers are not going, I mean, nothing is going to happen during the training stage. And once everything is converted into a transformer, after the fit function, the next function is the transform operation, which is the one predicting or computing the results. So as you can see, you can even mix in Spark and Spark NLP estimators. Like, for example, in this example, we have tokenizer stemmer from Spark NLP, and in the end, we wanted to use a stop word remover in order to do some TF, IDF inverse calculation or topic modeling with LDA. So everything is in the same page, and the idea is that there isn't much to learn. So when I did a benchmark, because I wanted to see how much Spark is contributing to the algorithms, even if they are self-included algorithms, there aren't any other dependencies, to see whether or how Spark NLP compared against a Spacey, for example, when we wanted to train something that was on HDFS, for example, and we wanted to train some data. So, well, the thing is that space is very, very, very fast when predicting and when working with like single shots of data and prediction. But maybe when you have a batch process that's going huge, or you want to train a model that has 13 billion tokens, for example, I know 2.6 megabytes might sound small, but in 2.6 megabytes we can have like plenty of billion of tokens. So it might be a lot for a model to train on those tokens, depending on which model we have. So for example, for parts of speech tagging, we have computed, and it scales much better when you increase the amount of data you have. So the good thing is that Spark, as you know, the idea of Spark is that you program your Spark job, and then you plug in a cluster, or you increase the number of nodes, and things are still working the same. And supposedly Spark is smart enough in order to design those plans, in order to shuffle into different nodes, do the operations, collect, map, reduce, whatever the task nature is. And the thing is that we prove that, of course, if we use a yarn client, the timings are much better, meaning that the algorithms can actually be distributed and take advantage of what Spark does. So the pipelines in Spark, as you know, are meant to be used with Spark datasets. That means that you fit on datasets and you transform on datasets. And Spark has a huge overhead. I mean, it's common nowadays to say Spark is good for everything. The real, when you get to work, is not good for everything. Spark is good for some specific problems, like everything else, even though it has a huge API and it works in many scenarios. For example, if you want to tokenize 10 sentences and you use Spark, you're overkilling the job, right? I mean, you go and you do Python, and it's going to be much faster. And if you have a single machine and you have a very specific job to do with sentences or tokens, then you do C++ or Python or Spacey, things like that are very fast. But if you have to do batch processing and maybe you have to fit many things in memory, then Spark is good, right? Because you put the dataset in memory, it's in RAM, it's going to distribute the task, and different nodes and different computers might be doing the job in parallel without you even knowing. But maybe you can run out of memory faster than common programs. So you have to be smart in Spark. So one thing we added in Spark NLP to kind of be able to experiment and train with examples is the light pipeline. Light pipeline is something completely the same thing than Spark ML pipeline, but the difference is that it's going to do the processing without specifically using Spark nodes. It's basically going to predict your sentence just so you get quick results without having to start Spark session clusters and things like that. So roughly a magic number I found is that for 40K rows in a document, light pipelines are much faster. And it comes like to the same speed of Spacey and things like that, and it's quite fast if you want to tokenize sentence detections, part of speech, everything. And well, you use Spark pipelines when you have a batch process you want to leave maybe overnight, or well, you want to make use of Spark because you know what you're doing, or you're supposed to know. Okay, so how things flow? Well, the idea of Spark NLP is that annotators we call to both estimators and transformers, are doing very specific things, like the tokenizer, or the normalizer, which is cleaning the tokens, or the parts of speech tag. And each one of them has a type and a requirement. So for example, the parts of speech needs text, so it can use either sentences or text. And it also needs some sort of tokenized version of that text. So as you get to know the annotators, you follow their requirements and you tell Spark NLP which column contains that information. So you go step by step, and the idea is to make it easy to use. So you can set up some parameters and things like that, go down to named entity recognition depending on their requirements. For example, the CRF model of NER that we have requires part of speech. So you must have a part of speech annotator in your pipeline. Okay. Let me go back for a second. So, well, the thing is that, of course, this is why you use machine learning. Well, it's when you want to tackle problems that are not following a simple rule or pattern. So machine learning is is capable of getting the implicits of your text. Okay, so I wanted to get down, how much I have 10 minutes, which is great because I wanted to focus this demo on showing an example of Spark NLP because that's what I like to target. I would like to know the library and would like to welcome to test it, feedback, and make things blow up, which usually happens, and also develop with us. I think it's a fun project. Okay, great. So the idea is that I was going to show you a live demo on my laptop, but then I realized that I was not going to use my laptop, so I exported the Jupyter notebook to HTML so I could share it. And bad thing is that I cannot run it with you, but it's there. And well, maybe I forgot to say, but Spark NLP has Java, Scala, and Python APIs, so the same as Spark itself, you can use it, and it's above the same, right? I mean, Python is usually a little bit slower because you need to serialize things and take them to the JVM and things like that we can discuss later. But nonetheless, it's the same API. So, okay, the first thing is that you import the libraries. Sorry for those maybe not really interested in coding, but I think it's a good thing. You import a library, like import the modules, like anything you do in Python, plus the other modules you do. The next step is that you start your Spark session, right? Maybe if you start Spark with PySpark, you already have a Spark session running, so you don't have to do that explicitly. But some people actually do Spark on pip, for example, and they start Python and then they import Spark and start it from within. So, well, in case you need it, it's like you would start Spark session normally. This is Spark 2.0, so maybe for those old users, the Spark Session Builder wasn't there, but don't worry. And then we start creating the pipeline of Spark NLP. So in this case, I'm going to show you a life science application that's going through two models, named entity recognition and assertion status. So I'm going to walk you through like how to build a pipeline with Spark NLP to solve that problem, meaning I have life science papers or documents, well, actually more clinical extractions, and I want to identify things like symptoms, symptoms, problems, specific conditional settings for clinical applications that refer to a patient. And assertion status is a problem that identifies in which state is that entity in. For example, if this situation, this healthcare situation is confirmed, it's a hypothesis, it's a conditional thing, it's something completely unrelated to the patient or things like that. So it's asserting some status on some entity. So that's why we are combining the two. So, well, the first and most basic annotator we have is a document assembler, which basically puts raw text into form of annotation, getting it ready for other annotators. Then we tokenize that text, meaning that we split it in words smartly, usually following some NLP standards like quotes and parentheses aside. We do normalization, meaning cleaning up tokens. And then we include a deep learning model that we have for named entity recognition, which in this case I'm loading it from disk, which is basically trained on I2V2 datasets. Those familiar with healthcare might probably know it. So it's basically a named entity recognition that identifies healthcare topics. And the next thing, well, I wanted to show in this example, I was not going to load an assertion status model. Instead, I was going to train it here with a very small and dumb data set. Okay, just 2 minutes. Thank you. And the thing about this example is that, as you will see, some annotators end with the word approach, meaning they are estimators somehow. So an approach is basically an annotator that requires training. So an approach will be converted into a model once it's trained. So in this case, I'm using the assertion logistic regression approach estimator, which has its own parameters. Like I need to tell it the context bounds I'm using, the embedding, the word embeddings I'm using, which in this case I'm using I2V2 word embeddings as well, and the label column, just like a Spark ML and estimators. And then the finisher, which basically cleans up a little bit things to make them human readable, because by default annotators output annotation structure, which have metadata, indexes, start and end boundaries of what matched, and lots of information you might not need. So usually the finisher gets what's important out of it. And then I put everything in a pipeline, like a big recycling machine or something like that. And well, then I create a data set, like clinical data set, like, I don't know, positive for shortness of breath, no cough, or some shortness of breath with allergies and things like that. So I just create a data frame and maybe a training data set which has some labels, some indexes about which parts of the sentence I want to assert. And then I fit. As you see, it's like the pipeline fit, training data. It will take some time. That will depend on your data set. In this case, the word embeddings file I'm using is 1.7 gigabytes, which is big. And for this, only this small training data set, which is only taking into account for the assertion approach, which is the only annotator in my pipeline that requires training. It's quite a small data set. It's five rows. But the word embeddings are 1.7 gigs, so it takes some time. And then I change, for example, as you know, Spark, I can change the parameters. So I can reset some settings, and I can set the assertion status to use NER output to assert. Because the assertion status asks the user, what do you want to assert? And usually you either have to provide some boundaries inside your sentence of what you want to assert, or you can use the NER output. For example, the NER found a problem, a healthcare problem, and then assertion status will assert that entity. There's also a small light pipeline example, which is easy to use. You just create light pipeline and you put your fit pipeline into it, and then you call function annotate and you pass a single sentence. And this will like parse it very quickly because it's meant to test small sentences or array of sentences. But of course, if you want to work with data sets, you go with the model as is and you call transform, and then you select the interesting columns. And then, well, for example, in this example, I'm showing the results of the assertion, which is basically asserting what the named entities found. So, of course, this model is not meant to be accurate. It's something I trained just as an example to get you an idea of how Spark NLP works. So, it's important that, I mean, it's understood that it's meant to be easy. Of course, it's never easy in action because you need to make sure your label data fits some format and you understand your annotators, you know its requirements, its parameters, and you configure things to your own thing. So that's wrapping it up. I think, thank you very much. And here in my last slide, I will put some contact information and also the GitHub link where you can follow with us, and feel free to follow with me later, so maybe we can even test it on the laptop or whatever you like. Thank you. Okay, so the question is, how is the performance compared to core NLP, and how it does for example, named entity recognition or stemmer, right? Is that the question? So the thing about training the models is that some annotators train with different kind of models. So you cannot have a single data set that works for training all of them. So many of them train with local data in your machine. And each annotator will take its own amount of time to train it. The good thing about Spark NLP beyond the training is that the prediction is 100% sure to be happening on the data set. And that means each computer or each Spark node is going to be predicting its own sentence. And that means for prediction, for all annotators, they are very fast for 2, 3, 5, 10 million rows in matter of seconds, because each node will be predicting its own sentence and things are distributed. For training, things are more complicated. I haven't tried core NLP, but for prediction, things are very fast on Spark NLP.
But if you use pre-trained model, because you guys have pre-trained model, right? So if we take your pre-trained model, and I take your sentiment detection, yes. Take your sentiment detection trained model.
Yes.
And I want to do like real-time streaming or near real-time streaming on it.
Yeah, so of course, every setting has its own setup. As I was saying, if you have a trained model, the prediction is, on average, very fast because the predictions are distributed and multi-threaded on Spark. If you take a sentiment analysis pre-trained model, you just load the model, which will take some time depending on how big the model is from disk. And once it's loaded on memory, Spark is going to predict it distributed manner. It's going to broadcast the information to all nodes.
I'm aware of. I've done some comparison with Core NLP, and I know that although it's distributed, it's still not that fast because it takes much time to load the model, run it. That is why I'm asking whether you have compared how much time it can take to process one HTML page. Let's say, like, I don't know.
Okay, I would say we can continue later because maybe there are other questions, but feel free to join and we can talk and test it together so we know. Any other questions? Maybe someone else? Yes?
Two questions. One, what exactly is distributed? Each annotator is distributed, and what's happening in training? How it's distributed in the training? The second thing is what already learned models do you have built in, and how do they compare related to the state of the art?
Okay. So the first question is, what does it mean distributing, and what are we distributing? So that follows the pattern of Spark, meaning that you have a driver in Spark that's doing the main computation. And the driver has the information about the pipeline, what are the stages of the pipelines, and a general information of the program you're running. When you execute the pipeline, either on fit or on prediction, that task is going to be computed on the nodes. And each node will have its piece of data that it knows, and it's going to work on that piece of data. Another node is going to work on another piece of data. Each annotators happen all sequentially, so normalization cannot start before all nodes have finished tokenization. But inside the annotation, inside the annotator, the annotation process is completely distributed. Of course, you need to manage your distribution because if you distribute too much, maybe you have overhead, so that's more strategy about what you want. Maybe depending on your data size as well, you want to know how much you want to distribute along the workload. But the other question, which is also very good, is what is it distributed when we are talking about training and prediction? So training is very difficult to distribute sometimes. For example, you have reinforced learning models that require constant updating information. And sometimes if you are distributing this model needs to know what are all the other nodes knowing about the model in that specific time. So there are models that are very hard to distribute, and depending on each annotator, which has its own algorithms to train, they are distributed some parts of it, all of it, and including some models that, for example, TensorFlow models, are directly training on some local machine in TensorFlow. So that varies along the annotators. And it would be great to add more annotators. The idea is to make it easy to include new algorithms. And it's easy, once you know your algorithm, to put it to work in Spark NLP. So that will vary a lot. Prediction is 100% distributed, means all the nodes will know the model. Yeah.
So at least for prediction, fundamentally the problem's embarrassingly parallel. Like you can distribute any machine learning model like this.
Yeah.
And so I wondered whether you see any advantage in, basically letting Spark take care of the map as opposed to, just having the job be, all right, load up some data from, a batch file, load up the model, do my work, and then export the results, which would be how I would tend to do it, because then you can actually manage the logic of, loading a different shard of data at different workers and things. So I wondered whether, it seems like this side of things seems simple, so I wondered whether you see an advantage in having that distribution sort of baked into the algorithm.
Yeah, that's a very, very good question. So the question is, what advantages I have of using Spark NLP that way when parallelizing the prediction as opposed to, I don't know, running some other sort of framework to just parallelize the batch processing, or maybe even I've seen many people use Spacey or Core NLP or Open NLP in Spark with UDF if they wanted to distribute, and that's perfectly fine. The advantages are very specific to the problem you're trying to solve. So many people have HDFS and have Parquet data and have a running Spark framework, and for that kind of people, Spark NLP applies very well because they don't have to change much of what they know. Other advantages are how you distribute your workload depending on what cluster you have, but also that when you try to put, for example, use Spark in UDF functions on Python, you have a huge overhead when serializing back and forth to the Java virtual machine, for example. So for some specific models and some amounts of data, it's more convenient to use it. It's a very difficult question, but it really depends on the problem you're having, what framework and technology you're already working on, and what are the advantages and disadvantages will vary depending on that, basically.
Okay, let's thank our speaker once again.
Thank you.